Was Ramanujan right or wrong for this expression? Well, let's derive this expression using a general term n to conclude whether he was right or wrong. But for that, please do like, share, subscribe my channel, and please support this video. Now let's start. So first of all, let's see the proof which is given by everyone to explain this problem. Well, let's see it. So everyone say that 3 is equal to root 9. Correct. So far so good. Then they said that it is equal to 1 plus 8. Okay. So far so good. Okay. So we can write it like 1 plus 2 times 4. We can write it like this. So it becomes 1 plus 2 and 4 can be written as root 16. Correct. Yeah. So we get 1 plus 2 root 1 plus 15. We can write it like this. Yeah. So we get 1 plus 2 root 1 plus 3 into 5. Correct. Yeah. So we get 1 plus 2 root 1 plus 3 root 25. Right. Okay. So we can write this expression as root 1 plus 2 root 1 plus 3 root 1 plus 24. We can write it like this. So we get 1 plus 2, this expression, then we get 1 plus 4 times 6, and again we can write it like roots 36, and this as 1 plus 35, and 35 as 5 times 7, right? And 7 as again root 14, and so on and so forth, right? But the problem is that how can we generalize this expression that it will always be of this pattern 2, 3, 4, 5, and so on? So to derive this expression, we should take an example using a general term n, which I am going to derive. So let's define a n such that n belongs to natural numbers. So n, it can be written as a square root of n square, correct? Yeah. So we can write it like 1 plus n square minus 1. We can write it like this, correct? So we get 1 plus n minus 1 into n plus 1. We can get this expression, means we get this expression, right? Okay. So we get 1 plus n minus 1 into the quantity n plus 1 whole square, right? Simple, right? So we get root 1 plus n minus 1 into the quantity n square plus 2n plus 1. We get this expression now, right? Okay. So we get over here 1 plus n minus 1 root, and we can take 1 over here. So we have 1 plus n square plus 2n, correct? Yeah. So we can further simplify this expression right over here. 1 plus n minus 1 into the quantity 1 plus n times n plus 2, correct? Simple, right? So we get root 1 plus n minus 1 into the quantity 1 plus n times the quantity n plus 2 whole square, right? Correct? Yeah. So we get 1 plus n minus 1 into the quantity 1 plus n root n square plus 4n plus 4, correct? Simple, right? So we get 1 plus n minus 1 into the quantity 1 plus n into the quantity 1 plus n square plus 4n plus 3. Now notice one thing, that this expression is factorizable and it becomes n plus 1 multiplied by n plus 3, right? So we can write it like this. It becomes n plus 1 into n plus 3, and so on and so forth. This series will go on. But why? Let's see the proof. So it is very simple. Like we can write n plus a whole square, right? Where a can be 0, 1, 2, 3, whatever value you want to take, right? So it becomes n square plus 2an plus a square, correct? Right. Now you have to take, you have to add and subtract 1, right? Because in the square root term there was a negative, there was a positive 1 term, right? Like it was 1 plus some expression, right? Like that we were doing. Okay. So let's add 1 and subtract 1. Let's do it. So we get 1 plus n square plus 2an plus n square minus 1, right? This is the expression. Now you can factorize this expression very easily. Let's see how. You get 1 plus n square plus a plus 1 plus a minus 1 n plus a square minus 1, correct? Okay, a plus 1 plus a minus 1 is 2a, and their product is a square minus 1, right? So it's correct. So we get 1 plus n square plus this expression, we get a plus 1 into n. We can write it like this, plus a minus 1 into the quantity n plus a minus 1 into a plus 1, right? Simple, right? So we get 1 plus this expression n times n plus a plus 1 plus the quantity a minus 1 into the quantity n plus a plus 1, right? Simple, okay. So we get 1 plus the quantity, we can take n plus a plus 1 as common. So you get n plus a plus 1 times the quantity n plus a minus 1, right? It is simple factorization, so I'm not telling that much. Basically, you're taking this and this common. It's basic, right? So you get from here that it is equal to 1 plus n plus a plus, n plus a minus 1 into n plus a plus 1, and again it is equal to 1 plus n plus a minus 1 into the quantity root n plus a plus 1 whole square, and this is what we needed to prove, right? Correct. And if you want, you can take the square root also, so it will become square root over here, and this is what we needed to prove, right? Simple. Understood? Understood not? So basically you got this expression, you start with this expression. So basically when you substitute a is equal to 0, you get root n square, which is n. So n is equal to root of n square, which is equal to this expression, and when a is equal to 0, it becomes 1 plus n minus 1 root n plus 1 whole square, and then you can apply the same logic which you applied over here, right? So instead of a, you can take a plus 1 over here, and the procedure will be similar. So it means that it can be written like this. It means the successive terms will be of this form only, means there will be always a square root term involved, and they will be always factorizable, which you proved with this general expression. So instead of a, if you substitute a plus 1, you will get over here a plus 2, and then here it will be n plus a, here it will be 1, and then this expression also, like we got that time, right, in proving for root n. So basically we can say that if you substitute n is equal to 3 and a is equal to 0, we get the expression as 3 is equal to root 9 is equal to this expression 1 plus 3 plus 0 minus 1 is 2 times the quantity 3 plus 0 plus 1 is 16. And if you apply this concept again, you substitute a is equal to 1, you will get this expression again. So you will get root 1 plus 2 root 1 plus 3 root 25, and so on and so forth. So this is the general method to prove for any n. So over here we have taken the values as n is equal to 3 and a is equal to 0. You can take any other values, right? It depends, whatever you want. So it is a general expression. So if we say suppose n is equal to 4, so in that case a, and assume that a is equal to 0, so you get 4 is equal to root 16, which is equal to the quantity 1 plus 3 root 25, which is equal to root 1 plus 3 root 1 plus 4 root 1 plus 5, and so on and so forth. Simple. So it means that using this method you can generalize this concept. So it means that Ramanujan was indeed correct. I don't know why when people give that proof in which they directly say that yeah, we can write like this, we can say that this expression is always becoming of the form of a square. So in that case many people get confused that how can we say that this will be always true. So this is the proof that why it will be always true, right? So this was missing in all the proof which I went through, so I thought to share you all this thing, right? So I hope so that you enjoyed this video. If you did, then please do like, share, subscribe my channel, and support this video. Bye bye, take care.